Sebastian alluded to, I did send out an email this morning. It's okay if you haven't seen it yet, about the midterm. So our midterm will run next Thursday evening at 6:30. I'll go over the details in the next slide. But before we do this, kind of in this digital world, there are certainly concerns among people across the university about academic dishonesty. So I just want to be very clear about, what the rules will be for this exam. So this will be an online exam. It will be open book, right? But that does not mean that you can represent other people's solutions as your own solutions, okay? It means you're going to have to use the materials that are available online to do the test individually to the best of your ability. A big part about being an engineer is accepting this ethical responsibility that we have, this, sort of responsibility to society, right? To sort of be building things on their behalf to make lives better. And I think that starts with, being academically honest here in your studies, right? So it's an online exam. You'll have access to everything on my courses, all the YouTube videos, but you will not be able to collaborate among each other, so the people taking the class, or among sort of external resources. So things like pay for solution services, which I'm sure we are all aware exist. So if you do that, and if we find that you've done that, then the consequences will be for this exam, you would get a 0. If it was on the final, then you would get an F in the course, right? And there's also notices of academic dishonesty stay on your record here at the university. So I hope, like I said, in the last year and a half, I've had to go through this more than I ever have in the rest of my career. But I'm hoping that we don't have to do anything this semester because everybody's going to be honest, right? Right. So the first midterm will be the Thursday, June 17th. So apparently either in the announcement or the email that I sent today, it might still say second midterm because I copied this over from an announcement from the fall. So it is the first midterm. It will begin at 6:30. Now, the way that this exam will be administered is potentially different than other midterms that you've had, even online midterms. So it'll be separated into 3 different parts, right? So the first part, nominally, so this will be different if someone has approved accommodations and lets me know that they want to use those accommodations on this exam. So the first part will be the multiple choice part of the exam. Normally, if this was in person, we sort of block each of these parts out to take about half an hour, but we'll give you a little bit more time than that for each of these parts, but they will all be done separately. So the multiple choice part of the exam will be available through the quiz portal on my courses. It will come available at 6:30 and must be submitted by 7:05 if you don't want to have a late penalty. Then between 7:05, between the multiple choice questions being due and the next problem coming available, you'll have 5 minutes. Kind of a time to rest, maybe recenter a little bit, right? Refocus. Maybe, run to the bathroom, get a glass of water, stuff like that. And then the next part of the exam will start at 7:10. Now, because here you'll actually have to, get the problem. You can print it out and work on the sheets that are there if you like. That's what we would do if it was a in-person exam. But if you just want to work online paper or whatever, that's fine too. But because you have to access the material and then submit it to a Dropbox just like you would with your homework, we'll give you 40 minutes for the 2 long answer problems. Whereas nominally we'd set aside half an hour to do these things. So that's an extra 10 minutes to kind of set up and submit a problem, right? In between the second and third problems, we'll also have this 5-minute break period so you can kind of recenter, right? When we first did this kind of gated exam, we made it so that it was not possible to submit anything after the rest period was over, right? But what we did for the second midterm and the final last fall, which I think is a good way to approach this, is that, so the multiple choice problem 1, in this case, would be due at 7:50. So if it's handed in between 7:50 and 7:55, there'd be a 10% penalty. Right? Now, if it's longer than 5 minutes late, then there'll be a 20% penalty, right? If it's longer than 10 minutes late, then, so it sort of goes up by 10. Do you need to print out the long answer? If we can't, what do we do? Yeah, so you'd hand it in like the homework, right? So you don't need to, you can just write on long line paper whatever your solution is, right? And then sort of scan it, like with Cam Scanner or however you do your homework, and then submit it. Right, so there's this kind of escalating penalty, 10% for every 5 minutes that it's late. I think that if you look at the announcement that's posted on my courses, it gives kind of an example of how that escalation works, just for clarity, but it didn't fit on this slide. So there's more details available in the announcement in the email that I sent you from the My Courses page. The other thing that I would like to do, since we didn't formalize the time before this, if you have any conflicts with this time, or you have university approved accommodations that you would like to use for this exam and subsequent exams in this course, please let me know and we'll make sure that that gets applied. It does mean, not that you have to worry about this, but then you'd have sort of a different Dropbox to use, because, and a different quiz to go into, because things will open and close at different times. Does anyone have questions about the format of the exam? Okay, so we've been talking about closed systems, right? So what we're going to talk about today, we're going to start to venture into the realm of open systems. Now, I always hesitate to say this because I'm not saying don't pay attention, but this material will not be on the first midterm, right? But we're going to move away from closed systems and into open systems today. But before we do that, I just want to, go over a bit of a refresher, give you a bit of a flow chart, a reminder of how to do these closed system problems, right? So we know that the first question that we want to ask when we're doing these first law problems is the system open or closed? And up until this point, and on the first exam, the answer to that question has always been, or will always be, if we're talking about the exam, that the system is closed. And because the system is closed, that means we use the closed version of the first law, right? That delta E is equal to Q minus W. If we make some assumptions, we can often turn that equation into delta U is equal to Q minus W. And then we find the work done in a particular process by understanding what the pressure-volume relationship is. And if we can cast pressure as a function of volume, then we know work is the integral of P dV. And then on the other side of the equation, for delta U, we remember that that's mass times the change in the specific internal energy, right? So this is the end point of the process minus the initial point of the process. But then we've got to ask ourselves, what's the fluid? Right? And we have two different possible answers for that. The first, which we probably have more experience with, is that the system is water, or at least something that's going to go back and forth across the vapor dome. In the future, we'll deal with things like refrigerants that do this too. But for the first midterm, we can sort of say, okay, it's going to be water or air. But really what that means is, something that's going to boil and condense, and an ideal gas, right? But if it's water or something like it, then we can either have liquid water, some two-phase mixture, a mixture of liquid and vapor that are both at the right conditions for phase change, but there's some mixture. It's not a complete liquid or a complete vapor. Or we can have superheated vapor. So that's all steam that's past whatever boiling temperature exists for the pressure that we're at. So this is where we draw those PV and TV diagrams and we try to figure out where on that graph we are, right? What's the right part, right? But our other option here, instead of water, we can have ideal gases. Now, if it's an ideal gas, that's still not enough. The good thing is if we answer, oh, it's an ideal gas, that means we can use the ideal gas law, just like we did in the problem last class. But we still have to decide if we're going to model the change in the specific internal energy as constant or variable specific heat. If it's constant specific heat, we'll never find the individual specific internal energies. Instead, what we'll do is we'll pretend or model that delta U term as CV, the specific heat at constant volume, times the change in temperature. If it's variable specific heat and we're dealing with air, then we'd go to something like table A22 and we'd use a temperature and we'd interpolate to find a specific internal energy. So what we're going to start to talk about today is what happens when the answer to this first question isn't that the system is closed. What if we're dealing with a system where mass can freely enter and leave our system, right? So here we're going to have three more questions that we're going to ask, right? But the first one is going to be what happens to the mass. Eventually, we're going to ask what happens to the energy. Eventually, we're still going to deal with a different version of the first law. But what we've really learned in this first module of the course is that mass itself has a means of storing energy, right? So if mass is coming in and out of our system, that means that energy must be coming in and out of our system with it. So our first step on the road to understanding what's happening with the energy, right? Because remember, thermodynamics is all about these energy transactions that are happening in the universe. So the first step towards understanding what happens to the energy is going to be what happens to the mass. Now, we didn't really talk about this for closed systems because in closed systems, what happens to the mass is nothing, right? It all just stays in the system, right? So when we talk about open systems, or sometimes I'll use the word control volume, right? Then this is a system where we draw this imaginary boundary, which is called a control surface, that envelops whatever our system is, right? So this is a sketch of an internal combustion engine, and it's an open system because there's air intake that's coming into the system, right? There's exhaust of air, right? It's not the exact same air. There's some chemical process that's going on in here. And there's also a fuel line that comes and feeds the engine, right? So this is an open system. There's air coming in, there's fuel coming in, and there's some kind of spent air fuel mixture that's going out of the exhaust, right? So this is an open system. So when we're dealing with open systems, there's a couple of things we have to do, right? So the first thing, this happens in closed systems too, we have to understand what are the boundaries of our control volume, right? So what's the boundaries of our system? What part of the universe are we interested in? Then we'll answer the question, what happens to the mass? And then once we know what happens to the mass, we can ask the question, what happens to the energy? Right? So the main focus of what we're going to talk about today is what happens to the mass. But before we get there, I want to talk a little bit about how do we draw control volumes. So this is supposed to be a sketch of a pipe, right? And really what we're doing here when we draw this control volume, right? I try to draw the boundary up against some solid part, right? So up against the inside of the pipe wall here. And then the porous parts, the part where mass can flow through, I try to draw that so it's perpendicular to the flow. So the flow comes right across. We're not going to do any kind of vector calculations here, but if you get into this habit, then when you start to deal in fluid mechanics and you try to find maybe forces or something that are acting on these boundaries of your control volume, it's a good habit to get into if you're drawing these lines perpendicular to the flow. So what happens to the mass? In this class, there's a few sort of core equations that we're interested in, right? We already talked about the first law of thermodynamics, right? This idea of conservation of energy. Another sort of bedrock idea in thermodynamics is that mass is conserved, right? So that the change in the amount of mass stored in a system over some time interval, we can figure that out if we just count all the mass that came in and all the mass that went out, right? So again, there's this kind of verbal definition, but I think the math here is more straightforward. Basically that the mass at the end minus the mass at the beginning is equal to all the mass that came in and all the mass that came out, right? I got my my teacup over here, right? If I take the lid off, it's empty right now. There's no mass in here. But if I put this out in the rain, right? Like it was pouring rain yesterday here, right? If I put this out in the rain, there'd be some mass coming in, right? Which would mean that my mass at the end would be more than my mass at the beginning, right? Now, this is pretty straightforward. I could tell this to my 3-year-old and she would kind of get it, right? But the problems do get a little bit more complicated. So we have this structure, this mathematics to sort of take care of it, right? So the change in the amount of system, the change in the mass stored in the system, that's what's on the left-hand side of the equation, is equal to, right? This is like the bouncer at the bar is counting how many people come in and how many people go out, right? Because there's some regulation about how many people can be in the bar, right? So, you know, we're gonna count all the people that come into the system, right? All the mass that comes into the system, and then all the mass that goes out. And the difference, well, the difference must be stored in the cup, right? So sometimes in this thing, this is what the words can sometimes be confusing. It just says the net inflow, right? That just means the difference between these two things, right? All the mass that comes in minus all the mass that goes out is the net inflow, right? If it's negative, I guess it would be outflow, right? So I like to draw pictures, right? Just like before, right? We had the universe, right? Which was like a gray blob on a blue blob in the background, right? The conservation of mass, right? My picture is this sort of branching pipe system, right? Or maybe it's like, veins inside your body or something, right? So the first thing we want to do is we draw our control volume. So where I can, I go across the solid walls of the system, right? Where it's impermeable to mass. But then I want to draw these lines that are perpendicular to the inlets and the outlets, right? Now, the way I'm thinking about this is that there's an inlet back here and there's 2 outlets back here. At time 0, right, my initial time, I have some amount of mass stored in this system, right? So that's my initial mass. That's M1 in this equation, right? And then I could take this system, and if I block that, let's say this was a pipe system, right? And it's filled with nothing, right? It's not filled with nothing. It's filled with air, right? So what happens is I block the 2 ends, right? So no mass can get out, right? So if no mass can get out, and I want to find out how much mass exists at the end, right? I can just add up all the mass that came in, right? And that means, right, this would be positive here on the right-hand side. That must mean that the mass at the end of the process is more than the mass at the beginning of the process, right? Hopefully that's pretty straightforward, right? Now this would be the equivalent of, I guess, your toilet when you flush it, right? The first thing that happens before the valve opens back up, right, is that there's no inlet fluid into the reservoir of the toilet, but the water rushes out of the reservoir, right? So in that case, there's no mass in, that's 0, but there is mass out, and that must mean that this right-hand side is a negative number. So that must mean the left-hand side is a negative number, and the mass stored in the system at the end of the process is smaller than the mass stored at the system at the beginning of the process, right? So we can find the mass at the end of the process if we know the inflows and the outflows, right? So this is conservation of mass. Sometimes, because we do this to ourselves, right? Sometimes there's shorthand and you got to bust out your engineering decoder ring, right? So sometimes instead of saying the words conservation of mass, someone will say continuity, the continuity equation. When they say that, they're talking about conservation of mass, right? It's just a fancy way. Because if we just said conservation of mass, normal people might be able to understand us, right? So this way we sound maybe smarter than we are, right? Right? Or it's just the lingo, right? You got to be able to understand the way that other people will talk about things, right? So here, conservation of mass or continuity, right? All we're saying is that, in this class, we're not changing mass directly into energy. We're not talking about nuclear reactions. So all the mass that comes in minus all the mass that goes out, I know the difference between those two things is equal to the amount of mass that I've stored or depleted in my system. Right? So that's what this equation says. Now, there is a special case, right? So let's say it's a nice Rochester day, so it's pouring rain outside, right? There's a lot of rain that's coming into my cup, right? Now, this is not clear, right? But normally, if my cup, if water was only going in, the water level in my cup would be going out, right? But let's say I drill a little hole in the bottom of my cup and it's exactly the right size that once I get to a specific water height, there's mass coming in and there's mass going out, but the amount of mass coming in is exactly the same as the amount of mass going out. In that case, the water level in the cup stays the same, right? So this is a special case that we call steady state. Now, what steady state means is that nothing is changing with time, right? So if nothing is changing with time, right, the only things in this problem are how fast mass is coming in, how fast mass is going out, and what the level of my cup is. So at steady state, all of those things are constant. None of them are changing, right? So even though something interesting is happening here, right, that there's mass coming in and there's mass going out, the mass in the cup stays the same, right? This is, practically, right, since you've, even if you're not from around Rochester, you've at least lived in Rochester through a winter, potentially, right? If you go into a car in the wintertime, right, you might say, I don't do this, but I know some people have like remote car starters. They let their car warm up to begin with, right? So when that happens, the car is pushing hot air into the cabin, but because it's cold outside, because it's a Rochester winter, there's heat escaping the car, right? Through like conduction through the windows or whatever, right? So there's heat that's leaving, but eventually, even though you're adding heat to the car and you're losing heat from the car, eventually the cabin temperature will get to some temperature and it will stay the same, right? And then you'll be at steady state, right? So this is the same thing here that, you can have mass coming into your cup and out of your cup and it stays the same, right? So there's two kinds of steady state. One of them is boring, right? The boring steady state is there's no mass coming in, there's no mass going out, and the mass stays the same. The interesting or potentially interesting steady state happens when things are still happening. There is mass going in, but it's the same amount of mass that's going out. So the water level is staying constant even though things are still happening, right? So if we're at steady state, nothing is changing, right? Now, one of those things is the amount of mass in the container. So even though it's different water molecules, the amount of mass is the same. So M2 is equal to M1, and that means that the left-hand side of my equation is equal to 0, right? So if the mass in my system is not changing, well, that must mean that the amount of mass that's coming into my system is equal to the amount of mass that's going out of my system. And like we said, this can happen in two different ways. The boring case of, well, both the mass in and the mass out are 0, right? But then the more interesting case where, well, things are coming in and things are going out, but those things are the same, right? So if we're at steady state, it means the sum of all the mass that comes in is equal to the sum of all the mass that goes out. So this, up until this point in this class, we've been talking about elapsed time version of equations. That these processes that we're talking about, we've been talking about like pistons in cylinders, compressing gas. So we've been talking about those things happening over time, right? But it turns out that for open systems, we don't usually think that way. Instead, for open systems, we think about what's going on in that nuclear power plant at a specific instant in time, right? So now instead of looking at elapsed time equations, we start to look at rate equations or instantaneous equations, right? Now, there could be alarm bells going off in your head. That means there's some calculus coming. And that's more or less true, but just to formulate the equations, right? So we tend not to do too much calculus in this class, although that'll come in heat transfer and fluid mechanics, right? But how do we construct a rate equation from this elapsed time equation, right? So maybe you remember this from math class, right? We're going to take all of these terms and we're going to divide them by some change in time, right? So there's going to be the mass in the system, the amount of mass, the change in the mass stored in the system divided by some time interval, right? The amount of mass coming into the system divided by a time interval. The amount of mass going out of the system divided by a time interval, right? And now what we do to construct sort of a rate equation is we say, well, what if that delta t, that time interval, is like super, super short, right? It's an infinitesimally small change in time, right? Then what happens is these terms become rate terms, right? Now, we're going to use a specific kind of notation because there's basically two different kinds of rate terms that we can talk about, right? So the ones we're going to write down like you'd see in calculus as d something by d something else. In this case, the mass stored in the system, right, by time, right? So dm by dt, that's going to be on the left-hand side of the equation. So that represents, when it's d something by dt, something that's stored or depleted in our system. So we can write that for the energy in our system, or we can write that for the mass in our system, right? But then we have these other terms. These terms are not about what's going on inside the system. These terms are about what's going on at the boundary of the system, right? So they're not talking about what's being stored or depleted in the system. Instead, this is talking about how much mass what's the rate? How fast is mass coming in at the inlet? And how fast is mass going out at the outlet, right? So even though all these terms would have the same units, right? Kilograms per second, for example, right? Some unit of mass divided by some unit of time, they kind of mean different things, right? So we denote them differently. Things that are happening at the boundary are typically given a dot, right? So this is another way in calculus that you sometimes represent d something by dt. But when we put a dot over something, what we mean is it's something that's not stored in our system, right? Or something that's happening at the boundary, right? So we got dm by dt is equal to the mass flow rate in minus the mass flow rate out, right? And the reason that we do this, well, I guess we'll see. I don't want to get ahead of myself here, right? So here, if we write out the words for this expression, right? This is no longer the change in the mass, right? This is how fast is the rate of mass changing, right? So if I was leaving my cup out in the rain and I knew how fast the mass was changing and I knew the density of the water, I could tell you something about, this isn't about what's the water level at one time and what's the water level at another time. This is about how fast is that water level moving up, right? Or how fast is that water level moving down, right? This is how fast am I storing the mass, or how fast am I depleting the mass? If you thought about this in terms of like your cell phone, right? Like this is, did you use the normal charger or did you use the fast charger that maybe came with your phone, right? So how fast is the system charging, right? How fast are we storing or depleting mass in our system? I don't know if that analogy worked, right? Right? So then this next term, this is going to be the sum of all the mass flow rates into the system, right? So, in that branching path that I showed before, which I'll show you again, right? There's only one inlet. So I only have to worry about one mass flow rate in, right? But there were two mass flow rates out, right? And those mass flow rates, there's two of them, right? So we got to add them together to get the total mass flow rate out, right? Right? And notice, in is positive and out is negative. Right? So this is, the sign convention here is as we're adding mass, that's positive, and as we're removing mass, that's negative, right? Or we could talk about the net inflow, right? That's just going to be the total right-hand side of this equation. But if we look at this pictorially, now we don't have to look at it at two different moments in time, right? Instead, we're taking a snapshot, right? What's happening at a particular instant, right? Now we're saying, how fast am I storing or depleting mass in my system, right? So that's my dm by dt term. Is this positive? Is it negative? Is it zero? I don't know, right? Could be anything, right? And then I've got, okay, how fast is mass coming in here at the inlet, right? And how fast is mass going out at these two outlets, right? And if I add all of those things together, I can figure out, am I storing mass or am I depleting mass? Right, so the change in the rate at which the mass is changing, right? So what's the rate at which the mass is changing is determined by the sum of all the mass flow rates in minus the sum of all the mass flow rates out. Now again, we can get to this kind of special case, right, where the water level in my cup is not changing even though there's mass coming in and there's mass going out, right? That's steady state. At steady state, nothing is changing, right? So what we look for at steady state, the reason that we have different notation for these different terms, right? Why the d something by dt terms are going to be talking about how much something is being stored or depleted in my system, right? The reason we do that is because then when we get to this condition of steady state, right, it means how fast is the mass in my system changing? Oh, it's not changing at all because we're at steady state, right? So then all these d something by dt terms go to zero at steady state. So at steady state, the rate of change of mass in the system has to be zero. But I can still have mass coming in and mass going out at whatever rates that's happening at, right? It's just those rates have to be balanced so that I'm getting the same sum of mass flow rates in has to equal the sum of the mass flow rates out. So that's why we keep the notation different, because the terms that are dm by dt, right, or later we'll see like de by dt, those terms go to zero when we are at steady state, right? And that makes our life better because there's no calculus, right? So this is the equivalent of, you've already turned on your car in the winter and it's already, warmed up. People say they get their car to warm up first, right? So they're not changing, right? Or it's, when you're, my dad and I don't know, they say you grow into your parents, right? So maybe I'm doing this too, right? But my dad's the guy on the highway, the 2-lane highway that pulls up and he's passing the truck on cruise control, like 1 or 2 miles per hour faster than the truck, right? So his car is at steady state and that truck is also at steady state, right? And it's just moving past it, right? But me, at least 20-year-old me, when I was passing that truck, I was not at steady state, right? My foot was much closer to the floor, right? And I was getting by that truck as fast as I could, right? So that was not steady state, right? Because I'm accelerating, right? So something is changing with time, right? So here's our equation, right? Is dm by dt is equal to the sum of the mass flow rates in minus the sum of the mass flow rates out, right? So we got one equation and we've got 3 unknowns, right? So what we'll do, right, a lot of times in this class in particular, right, maybe when you go to Thermo 2, this won't be the case, but in a lot of problems in this class, we'll be worried about steady state. Steady state's really important in a lot of problems, right? So like nuclear power plants, the idea is you kind of turn them on and you just leave them, right? So a lot of times they're running at steady state, right? When you're at cruising altitude in a plane, you're probably more or less at steady state versus when you're taking off, right? Then you're not at steady state. But most of the journey, you're probably more or less at steady state, right? So, if we're at steady state, the beauty is that this term goes to zero, right? We don't have to use something like separation of variables or anything. But then how do we deal with these mass flow rate terms, right? How do I put those in, right? Because some problems will tell me, oh, there's some mass flow rate, right? But some problems you won't. Maybe you'll have to figure it out, right? Maybe you'll have to fix states, right? Because we've been doing that a lot, right? That's maybe some foreshadowing, right? Right, so if we look at flow in a pipe, you won't learn this until you're in fluid mechanics, right? But flow in a pipe, the way that we model it is we say that the fluid, we think about the fluid as lots of little pieces, right? Even though it's some continuous medium, we think about it as having lots of different fluid elements, right? We almost like digitize it. right? And the fluid elements that are closest to the wall, we say that they have this no slip condition. That, the water in the middle of the tube, it's free to move throughout the whole thing, right? It's going pretty fast. Those water, elements that are stuck against the side, they're just stuck there, right? They can't move, right? They're like, I don't know, Luke's aunt and uncle on Tatooine, right? They're never getting out, right? So they just stay there, right? But there's fluid in the middle that's moving through, right? So you have some kind of shape. If you plotted the velocity as a function of the radius in the tube, it would look something like that, right? Now, we got a lot of different variables here. We can talk about the speed, right? That's just the scalar version, right, of the velocity, right? We can have velocity because speeds have directions too. We can talk about this v with a bar over it, right? That's average speed. Sometimes I use volume. So this is why sometimes I cross my v's here to denote volume, because, in some problems, you can have a volume, you can have a velocity, you could even have a voltage if you were heating the fluid in this pipe, right? So, sometimes we only have one letter, right? So for right now, we're going to talk about volumes with a cross through them, right? So that's going to be my volume. And then my specific volume, we know about this, right? This is volume divided by mass, right? Here, this liquid is going to have a density. That's 1 divided by the specific volume. There's a cross-sectional area of this pipe, right? So if I took a bandsaw and just cut through it, right? It looks like a circle. There's our radial position, right? Our coordinate system. Then there's also the radius of the pipe, right? So our coordinate system goes from 0 to big R, right? And what we would like to know is the mass flow rate through the pipe, right? So what we could do is we could, because there's some velocity distribution in the pipe. So what we could do is we could integrate along the pipe and we could find the mass flow rate. So the mass flow rate, if we wrote it out in sort of mathematically, right, we would have the integral from 0 to big R of density times velocity as a function of R times dA. So I guess this should go from 0 to A, right? And there really are two integrals here. So one you'd be integrating with the radius, and the other you'd be integrating along the azimuthal direction. So in theta, you'd also be integrating, right? Right, so here, because theta just goes from 0 to 2 pi, right? So this goes density times velocity, which is a function of the radius, times 2 pi r times dr, right? Now, I don't expect you to have to derive this equation, but I want to kind of show you that I'm not just making this up, right? We start with kilograms per second, right? This is always a good thing if you're not sure about your equations, right? We think it's a mass flow rate, so that's kilograms per second. We have density, which is kilograms per meter cubed, multiplied by velocity, right, which is meters per second, multiplied by area, right? So this meters per second times area is like meters cubed per second. Sometimes we might call that a volumetric flow rate, right? What's the volume of mass coming into the system and going out of the system, right? Now my equation looks a little different, right? But I still get the same units, right? So that's good, right? I can't convince myself that my equation is wrong anyway. Right, so let's make an assumption, right? Let's make our lives a little bit easier. The best calculus is when the answer is 0, right? But the second best calculus is going to be when something is constant, right? So let's pretend, even though we know that velocity could be a function of the radius, what if it's not, right? If it's not, then I can just take the density times not this velocity distribution, but like the average velocity. So I could find the average velocity, if this pipe, let's say I turn my hose on and I have a pail and I know the volume of the pail, right? I could, figure out how long it takes to fill up that pail. And then I could find the velocity of the fluid coming out of the pipe, right? The average velocity, right? But without putting in, some sort of way to measure this velocity here and, taking measurements at different parts along the pipe, I can't really know the velocity distribution, right? At least experimentally, right? So here, right, I could say this, right? and then I could integrate from 0 to r, 0 to r from r dr, right? And then I get this, right? That the mass flow rate is equal to the density times the average velocity times the area, right? And in this case, because the cross-section is a circle, that area, the cross-sectional area of my pipe, is pi r, big R, right? The actual inner radius of the pipe squared, right? Now, because this is thermodynamics class, we don't talk about densities, we talk about specific volumes, right? So our mass flow rate equation that we'll typically use is going to be the mass flow rate is equal to the average velocity times the area divided by the specific volume, right? So that equation is going to be pretty important for us, right? But you can see here, right, that sometimes we're going to have to fix the states, right? At all the inlets and all the outlets, we're going to have to know what the specific volume is, right? So we're going to have to fix the states, right? Because the density will not be constant, because a lot of times, right, we're talking about like steam engines, right? So a lot of times we'll have water coming in and steam going out, right? If it was just water coming in and water going out, well, the density is pretty constant, right? Even if the temperature changes. If it's liquid, it doesn't really change the density that much. But if I have water coming in and steam going out, the density changes by about a factor of 1,000, right? So that's pretty important, right? You'll get definitely the wrong answer if you don't account for the fact that the specific volumes are going to be changing in these problems. But to get to this equation, we had to come to this assumption. We had to write down this assumption that the velocity in the pipe was approximately constant. Now, is that a reasonable thing or not, right? Maybe you've heard of something called turbulence. Turbulence is this sort of chaotic mixing of flow, right? And it happens as flow gets faster. If you think about, I don't know, you ever played Crack the Whip as a kid, right? Maybe this is, I don't know if it's a Canadian thing or not, right? Skating on ice, right? And you're holding hands with the people, right? And there's somebody that's standing kind of at the center and you're running around, right? You're like rolling around, right? And what happens is the stress changes as you get further away in the radius, right? The same thing happens, right? And eventually the whip cracks, right? Somebody's grip fails, right? And all the kids fall down, right? This is what we did before the internet, right? Right? But here, what happens is the same sort of thing happens in this flow, right? If you go to the tap in, say, your kitchen, and you turn the flow on just a little bit, right? You'll see that the flow is kind of slow, but it's like beautifully clear. You can look through it. Now, maybe it's got some kind of curvature, so maybe it distorts the image, but it's nice and clear, right? Now, if you crank that tap up, right, what happens is that, no, it doesn't involve, that's a different class, right? So if you turn that tap up, right, then what's going to happen is the flow starts to look, it looks like there's bubbles and stuff in the flow. So what happens is, you know, there's these fluid elements that are stuck against the wall, right? And there's the fluid elements in the middle that are moving very quickly, right? And so what happens is the fluid elements kind of like stretch, right, this way. They kind of like rotate. And what happens is eventually that that flow goes faster and faster and faster. And those elements, you know, they got a side on one side going really slow and a side on the other side going really fast. And they start to actually turn, right? So what happens is they kind of spin out, right? So these guys over here, they start to kind of spin out to the side. So they don't just have a velocity down the pipe anymore. Now they've got this kind of rotating motion inside the pipe here, right? So when you're in fluid mechanics class, you might end up disliking turbulence because the math is like really hard, because there's like a randomness to this, right? This is, you know, we talked about if you're picking classes and something is called like nonlinear or something, like nonlinear controls. That's sort of code for controls but harder. Our engineering decoding word for this randomness, because you don't want to say, oh, that's just random, right? Because then somebody maybe thinks like, oh, you're just not smart enough to figure it out, right? So instead, we use the word stochastic because nobody knows what that word means, right? So if you take a class and it says stochastic something, right? Stochastic modeling, right? What that means is you're trying to make a computer program that tries to code for randomness, right? Now, one application of stochastic modeling is looking at turbulent flows, right? So what's going on in turbulence? Because even though we know what's going on in the average sense, discretely, it's hard to know exactly what's happening at any given time, right? Another stochastic process is the movement of the stock market, right? So when I was in my PhD, there were modeling guys that, that were modeling turbulence, but there was a group that came in from, one of the big investment firms, and they were looking for, it was like a career fair kind of thing. And they were looking for people who could model these kind of stochastic processes, not because they were interested in fluid mechanics, because they wanted people to sort of try to develop better models for trying to predict what's going on in the market, right? Which is, in the long-term average, generally pretty stable, but any given, instant in time, who knows what's happening, right? So the good news is with turbulence, even though the math is hard, the good news is it moves from something that's more of this parabolic curve that we associate with laminar flow. That's laminar flow, that's kind of slow flow, right? To now when you crank your tap open and it gets very chaotic in here, now it's turbulent flow and the velocity profile is much flatter, because what happens is the fast flow at the edge or in the center starts to move out to the edge, which gives you more of an average, more of a flat velocity profile. So this assumption that the velocity profile is approximately constant, it's not terrible, especially for practical engineering applications. It's a pretty reasonable approximation, right? We like this in heat transfer too, because it tends to, turbulence happens at faster velocities and you get better mixing in the flow. So you tend to get much better heat transfer in turbulent flows. So if that's something that you're interested in, it's also good, right? But you'll learn that in 2 years, right? So we have this equation, conservation of mass, right? We can take these mass flow rate terms, the m dot terms, and change them into the average velocity times the area divided by the specific volume, right? So now my equations look like this, right? So I get that the rate at which mass is being stored or depleted in my system is the sum at the inlets of the average velocities times the area of the inlets divided by the specific volume at each inlet, minus the sum of the velocities at all the outlets times the area at all the outlets divided by the specific volume at all the outlets. Right? So, so this is now what our conservation of mass equation looks like. So if we know the inlet velocity and we know the area, or sometimes a problem will tell you the volumetric flow rate, right? The volumetric flow rate is velocity times area. So we could also write this as V dot, right? Capital V dot would be volumetric flow rate divided by specific volume, right? That's another way to write that expression. We can still have steady state when we write the equation this way, and then we get that the dm by dt would be equal to 0. So the sum of all the mass flow rates in is equal to the sum of all the mass flow rates out. Right, so that's basically all we're talking about today, just this idea that, that we can store and deplete mass in a system, but for open systems, we're typically looking at the rate version of the equation. So we need to know what are the properties, like the velocity and the specific volume, and how big, like what's the area of the inlet. And when we have an outlet, we also need to know the velocity, the area, and the specific volume at the outlet, right? And like we said, when we're talking about steam engines, you can have dramatically different specific volumes at the inlet, right? So maybe it's water and the specific volume is 1/1,000, right? But then when you get to steam, it's like 1.5, right? Or 2, right? So you can have dramatically different specific volumes. So just because you know the volumetric flow rates doesn't necessarily mean you know anything about the mass flow rates, right? So mass is conserved, but volume is not conserved. Right? We'll do some examples next class. So that's all that I had for you today. If you have any questions, I'm happy to stick around for a couple of minutes. Otherwise, have a great day.
Have a great rest of your day.
Thanks, you too.
Thank you, Professor.
No problem.